All right, good afternoon. Just picking up where we have been working with, once again, functions and polynomials. And we've been working with polynomial division and started looking into domain as well as vertical asymptotes. We're just taking just a little bit of a step back regarding polynomial division, where we have looking at forming polynomials from given zeros and their multiplicity as well as an assigned degree. And we have on page 281, okay, now we have in the case of problem 72, now we have three distinct zeros, and each of these will have a multiplicity of 1, and the degree of the polynomial formed is going to be at 3. And looking at forming a polynomial with these characteristics, so if I start out with the factored form of the polynomial, so we have here, we'll say that the polynomial is going to be f of x, and from the respective zeros, we have with 1, okay, we can say we have the factor that corresponds will be at x minus 1. For negative 6, we can say that this will stem from x plus 6. And in the case of 3, we can say that this will originate from the binomial x minus 3. Okay, so this is a factored form. And as we look at establishing an expanded form, okay, where we have the leading term is going to be third order in x. So we can continue, okay, and in the process, okay, if I multiply, let's say, the first two expressed binomials, so we have with the quantity of x minus 1 times that of x plus 6, we're going to have x squared, and the outside and inside products will combine, where we have 6x minus x becomes 5x, and we have for the last product, okay, this will be at negative 6, and then we have times the quantity of x minus 3. And in terms of the follow through, and you could set up the multiplication in a matrix form, whether it's like a 2 by 3 or a 3 by 2, and we'll let this be a 2 by 3. 2 is in number of row headings, 3 is in the number of column headings. Okay, so we have looking at what we have in multiplying. Okay, so you're going to have 2 rows and 3 columns. And just looking at taking what I have and just sectioning for the moment. Okay, so we have in the case of the first product, okay, looking at what we have with the first column. So we have x squared times x becomes x to the third. And moving down, okay, we have negative 3 times x squared. And then we have with the next column, we have x times 5x. So this is going to be 5x squared. And moving down, we have 5x times negative 3, so this will be negative 15x. And then we have with the third and last column, okay, we have at the top, we have the product negative 6x. And the last product, we have negative 6 times negative 3, which will result as positive 18. So we have for a third order polynomial that will have these zeros. In other words, we have 3 solutions at x equal to 1 as well as negative 6 and positive 3. And that will exist as a polynomial of third degree. Okay, so we have combining, okay, so you have x cubed is the only third order term. And then we have in second order, we have negative 3x squared plus 5x squared. So that will form 2x squared. And then we have for the first order terms in x, so I have negative 15x and a minus 6x. So this will be a negative 21x. And finally I have plus 18. Alright, now for the case in 74, okay, now there will exist a non-integer 0 in the mix. And for this problem, okay, so you have 3 distinct zeros, and the first two will have a multiplicity of 1, and the last one is going to have a multiplicity of 3. So those that have a multiplicity of 1, we have 2 and 5 halves, and then we have with 0, 0 is going to have a multiplicity of 3. And the degree of the polynomial, okay, that is going to be at 5. Okay, and so, in other words, 0 is going to correspond to a factor that will be of third order. 5 halves and 2 will have each factors that will have 1 as the degree. So you've got 1 plus 1 plus 3 in the multiplicities, and that will add up to the 5th degree. So looking at establishing a factored form, so you have f of x. Now for 2, I have x minus 2. For 5 halves, I can start out with x minus 5 halves. And from 0, now I have just x for now. And since 0 is a 0 with a multiplicity of 3, the corresponding factor will not be just x, but x raised to the third. And now I can multiply these terms as they are presented throughout. But again, I can also rewrite the setup whereupon I can undo the presence of the fraction 5 halves. So I can raise the coefficients in the case of the second binomial expression. So what I can do here is I can multiply x minus 5 halves by 2. And in the follow-through case, I have f of x is equal to, and I have the quantity of x minus 2. And then we have 2 over x minus 5 halves. Okay, this will be 2x minus 5. And once again, I have x to the third. And multiplying what we have throughout. And if we look at just the first two factors, so taking the FOIL, okay, so you have x times 2x will become 2x squared. Outside product we have at negative 5x. Inside product we have at negative 4x. Combining negative 5x with negative 4x, we will have negative 9x. And negative 2 times negative 5 is going to be positive 10. And again, we have multiplying by x to the third. So one possible 5th order polynomial that if you were to set equal to 0 would have these zeros, including 0 with a multiplicity of 3. Okay, we would have 2x to the 5th minus 9x to the 4th plus 10 times x to the 3rd. This is one possible answer. And had I kept the original expression, and just multiplying what we have at the moment. So we have for f of x, if I just work with the original expression, so without modifying the factor in the middle. So I have x squared. Outside product is going to be negative 5 halves x. Inside product will be at negative 2x. So I have negative 5 halves minus 4 halves from minus 2. Okay, so So we have x squared minus 9 halves of x. And the last product, so we have negative 2 times negative 5 halves, and this will be a positive 5. And once again, multiplied by x to the third. So another way that you can arrive at the result is having kept the factors as they originally were. And so for this output, okay, we have x to the fifth minus 9 halves times x to the fourth, and we have plus 5 times x to the third. The only difference between these two answers, two versions of the answer, is just a factor of 2, where this layout is, again, twice the result had I kept the factors as they were originally on display. Okay, now.
I didn't get that. Could you try again?
No. All right. Sorry about that. Okay, now in the case of what we have regarding domain and asymptotes, and we have just crossing over to what we have in the case of number 7 for the next group, and we have in this particular layout, and we have in the mix. Okay. So we have for number 7, okay, so we have a given function f of x is equal to x squared minus 25 and we have all over x minus 5. Okay, now if we're looking, say, for both the domain and any possible asymptotes vertically. Okay, so we have for f of x, so I have x squared minus 25 over x minus 5. And again, for the domain, okay, now again, for a rational expression, the denominator cannot be equal to 0. So for x minus 5, this part here, if that cannot be equal to 0, but we have the x cannot be equal to 5. So we have, in the case of the domain, okay, so for the first half, we have those values of x less than 5, and we have for the second half, we will have those values of x greater than 5. So that would be the domain. Now, looking at what we have in the case of f of x, once again, now if we're looking for what's going to happen once we simplify, okay, so I have x squared minus 25 over x minus 5, and if I look at factoring, so we have a difference of squares in the numerator. So I have x plus and x minus 5 all over x minus 5. And if you notice, we have the denominator, x minus 5, is going to cancel. Okay, since x minus 5 cancels completely, okay, this means that instead of being a vertical asymptote, x equals 5 is going to be a hole in the graph. And for this particular function, now this is going to reduce to x plus 5. And if you notice, okay, there is no denominator factor. In the variable x. So since there is no denominator factor in the variable x, this is going to mean that there is no vertical asymptote. No VA, as in vertical asymptote. So there does not exist a vertical asymptote. And just looking at what we have from a visual standpoint, Okay. So if I were to graph, okay, so there is no vertical asymptote, so there's not going to be a vertical dividing line. Instead, what we're going to have, let's see, let me do it this way. See, once we get to x is equal to 5, instead of the graph running continuously, okay, there's going to be a hole at that location. And for the graph of f of x is equal to x squared minus 25 over x minus 5, it's going to be the same as if you had y is equal to x plus 5. But the only difference is that with the restriction from the domain, okay, you're going to have a hole at x is equal to 5. Now, in the case of what we have with number 7, going from number 7 to number 8, okay, we have here, okay, we have the function whereupon we have g of x is equal to x squared minus 9 all over x minus 3. And again, for g of x to be defined, okay, the denominator cannot be 0. So the denominator, we have x minus 3. And if that cannot be 0, well, we have that x cannot be equal to 3. And so for what we have in the case of the domain, okay, so you have only one exclusion this time with 3, so the domain will be those values of x less than 3 along with those values that will be greater than 3. And looking at what we have in reducing this rational function, so we have x squared minus 9 all over x minus 3. And we have once again in the numerator a difference of squares. So x squared minus 9 factors out to x plus 3 and x minus 3. And we have over x minus 3. And again, you're going to have the denominator expression to cancel out completely. Okay, so you're going to have in this case, all right, so you're going to have over here, I don't know what, give me just a moment. Okay, so we have x minus 3 is going to cancel completely. And just like x equals 5 earlier, okay, x equals 3 is a whole. And g of x, okay, so this will reduce to x plus 3. And once again, okay, just taking what we have in the graph of g of x. Once again, we have a hole located at x equals 3. And so we have for this function, g of x. Okay, that's going to be almost the same, in fact, except for the hole at x is equal to 3, the graph of g of x would be the same as y is equal to x plus 3. All right. Now, okay, so neither number 7 nor number 8 had a vertical asymptote. Now, for the next set of items, okay, we have for number 17 and 18. Now, both of these functions will be in simplified form. And for the case in number 17, okay, so we have f of x is equal to 8 over x minus 4 now I'll just mention, okay, so we have f of x is already in simplest form. Now, regarding the domain, once again, the denominator cannot be equal to 0. So that means that 4 is going to be left out of the domain. And so we have with the domain, okay, we have, again, just first half, you have those values of x less than 4. And for the second half, we have those values of x that will be greater than 4. Okay. And since the function is already in simplest form, okay, so this means that we have that x minus 4 remains, as in not canceling out. And since the denominator factor remains, this means that the exclusion from the domain is going to define, okay, the vertical asymptote. And for the vertical asymptote, again, the restricted value, we'll set x equal to this. So you have a vertical asymptote at x is equal to 4. And this time we have with the graph of the function. Okay, so we have a vertical asymptote at x is equal to 4. And in terms of the graph of f of x, okay, so this can be divided up into 2 sections here. And again, for the correspondence between the graph of the function and the vertical asymptote, okay, there will be no contact with any vertical asymptote. And we have f of x equals 8 over x minus 4. Okay, that will be split up into 2 distinct regions, okay, where the split up is done by the vertical asymptote x is equal to 4. Now, In the case of number 18, we have the function g of x, okay, is equal to 2 over x plus 7. And to keep this function defined, again, x plus 7 cannot be 0. So we have excluded from the domain the value of negative 7. So we have with the domain, we have those values of x less than negative 7, along with those values of x that will be greater than negative 7. And for what we have in the case of g of x, okay, so that is already going to be in simplest form. Alright, so g of x is already in simplest form. Okay, so the denominator x plus 7 is going to remain. So this means that what we have excluded from the domain, that is going to be converted to a vertical asymptote. Alright, so just looking at what we have once again. So we have a vertical asymptote at x is equal to negative 7. And for the graph of g of x, once again, this will be split up into two separate regions. And once again, neither section comes into contact with x is equal to negative 7, or whatever the vertical asymptote happens to be. Alright, so 17 and 18, those functions are already in simplest form. Now for number 20, now this one is a bit of a tricky item, for this is one, while already in simplest form, looking for the domain, okay, is a little bit of a quite a bit more of an exercise, at least in comparison to 17 and 18. And just to give you a bit of backdrop, okay, so we have for number 20, so we have a function k of x is equal to x plus 2 and we have all over 3x squared plus 8x minus 3. Okay, if you notice in the denominator, okay, have 3x squared plus 8x minus 3. And this is one that we can factor. And so just kind of stepping to the side here. So we have a 3x squared plus 8x minus 3. Okay. Again, you can use trial and error since we have relatively low valued coefficients. But we'll do the factoring by grouping on this one. Okay, so if we go with the first and the last coefficients, so you have 3 times negative 3 is negative 9. And again, if we look for the factors of negative 9 whose sum or difference will be on the plus side at 8. Okay. So again, we started out with 3 and negative 3. However, 3 and negative 3 add up to 0. But we want positive 8 for the sum. So we'll have more weight given to the positive factor than to the negative. Now, so I'll put the negative out at the front. So you have minus 1 and plus 1. Plus 9 rather. Negative 1 times 9 is negative 9. Now negative 1 plus 9 comes out to 8. And using what I have for the coefficients, negative 1 and 9. So I'm going to split up the 8x Okay, now I could put the plus 9x at the front of the minus x, but I want the middle operation to be addition as much as possible, especially without having to concentrate so much with factoring out negatives. And by placing the positive afterwards, it takes a bit of less work involved. So I have negative x, and we have plus 9x minus 3. And looking at grouping, okay, so you have 3x squared minus x at the front. And we have addition in the middle. And just go ahead and put parentheses around 9x minus 3. Notice there's no change up in the signs. Okay, and looking at drawing out, okay, the greatest common factors. For 3x squared minus x, greatest common factor is going to be at x, and into the quantity of 3x squared minus x. Okay, so this is going to be x times the quantity of 3x minus 1. And I have plus greatest common factor of 9x and negative 3. Okay, that is going to be at 3. And taking 3 into the quantity of 9x minus 3. Okay, this is going to be 3x minus 1. So for factoring what we have in the denominator, we have the common binomial between the groups at 3x minus 1, and the other factor will steal from the outside terms and the operation of addition. Okay, so you have x plus 3. Now, looking at what we have for problem 20. Okay, so again, this is our original function. And again, for the function to be defined, okay, the denominator cannot be equal to 0. And if that is the case, then neither factor can be 0 either. And again, the factors we had at 3x minus 1 and x plus 3. Again, neither factor can be 0. So I have 3x minus 1 cannot be 0. And we have x plus 3 cannot be 0. And if 3x minus 1 cannot be 0, we have 3x cannot be 1. And so we have the x cannot be 1/3. As for x plus 3, if that cannot be 0, but we had the x cannot be negative 3. So we have, in the case of the domain of k of x, okay, so we're starting from negative infinity, approaching the smaller of the exclusions. In this case, this will be negative 3. And you have followed by those values of x greater than negative 3 and less than 1/3. And then we'll have those values of x, okay, which will be greater than 1/3. Okay. And as for what we have in the case of the determination of vertical asymptotes, so again, we have k of x equal to this ratio, and we have, looking at the factored form, we have the quantity of 3x minus 1 times that of x plus 3. And notice that there is no cancellation since there is no 3x minus 1 or x plus 3 in the numerator. Okay, so this signals that we have both 3x minus 1 and x plus 3 to remain. And in terms of what this is going to mean, okay, we have two exclusions from the domain, and since we don't have any cancellation of factors in the denominator, we're going to have two vertical asymptotes. Okay, so we're going to have one at x is equal to 1/3, and the other we have at x is equal to -3. So for what we have in terms of the overall picture, again, we have on the x-axis, we have the values of interest. Okay, we have at -3, and also we have at 1/3. And again, we have vertical asymptotes running through the x-axis at those assigned values. So we have again x equal to -1/3 and x equal to 1/3. And just for the nature of the graph of x of x, k of x, okay, so we're going to have not just two, but instead 3 partition sections. And again, the vertical asymptotes are going to be off limits. Okay, so this is what we have generally, okay, for k of x. And again, you have that function we have split up into 3 distinct sections. All right, and we'll be looking into cases involving other types of asymptotes. And I'll tell you what, just for the next few moments, okay, let's see what we get when determining the domain and vertical asymptotes and say we have for this function r of x is equal to x squared minus 25 all over x squared plus 7x plus 10. Okay, so looking for the domain and the vertical asymptotes of this rational function. Okay. Again, we have with r of x equal to x squared minus 25 all over x squared plus 7x plus 10. Again, the denominator cannot be equal to 0 for r of x to be defined. Okay. And we have with the factors of x squared plus 7x plus 10. Okay, we have x plus 5 as well as x plus 2. So if x plus 5 cannot be 0, can we have that x cannot be negative 5? As for x plus 2, since that is not allowed to be 0, we have that x cannot be negative 2. So we have, once again, two exclusions from the domain. Okay, so starting from negative infinity, okay, so you have going from negative infinity approaching but not including negative 5. We have bypassing negative 5. Okay, in the next group we have those values of x greater than negative 5 and less than negative 2. So just like negative 5, negative 2 is going to be bypassed. And the rest of the set, you have those values of x greater than negative 2. So that will be the display of the domain in interval notation. Now, for what we have regarding the reduction of this rational function expression. Okay, so kind of like the very early problems, the numerator consists of a difference of squares. So for x squared minus 25, okay, we have x plus 5 and x minus 5. Okay, and for what we have in the case of x squared plus 7x plus 10, okay, we have factoring, okay, we have x plus 5, as well as x plus 2. So we're going to have x plus 5 to cancel out. Okay, so x plus 5 completely cancels. So we have the x equals negative 5 is going to be a whole. And for the rational function, now the completely reduced form comes down to x minus 5 all over x plus 2. Okay. And so x plus 2 remains. And since that factor remains, that means that we're going to have a vertical asymptote at x is equal to negative 2. And just for what we have in the case of the layout, once again we have with the restricted values of interest. Okay, so you have negative 5 as well as negative 2. And again, we have a vertical asymptote at x is equal to negative 2. And just for the graph here, for R of x, okay, so you have a lower into the right section. Then for the section that is running up, and in the left hand section, okay, again we have x equals -5. Okay, there'll be a location of a hole. So you have a hole at x equal to -5. Again, for the rest of the graph of R of x, okay, again you have running tangent to the vertical asymptote, x is equal to -2. Okay, so again you have two exclusions from the domain, and the destination is either it's going to be a vertical asymptote, and it will be a vertical asymptote if the corresponding factor does not cancel. But if it does cancel out completely, then it becomes a hole in the graph. All right, and again, so along with domain and vertical asymptotes, okay, there is going to be another group of asymptotes apart from those that run vertically, and we'll have, in the case of horizontal and slant asymptotes. Now for the introduction of these items, for horizontal and slant asymptotes, I'm going to reintroduce that polynomial notation that we had when we were working with end behavior, as well as polynomial division, like that led to the long division as well as the synthetic division. Now for what we have regarding horizontal and slant asymptotes, so we have for a rational function, and we have R of x. Okay, so we have again, we have a fraction on display. Now the numerator will be like what we saw in the past with your a of n times x to the n, and then we have a of n minus 1 times x to the n minus 1. We have running down to a constant, which we have at a naught. And then this is going to be over, okay, another polynomial. And here we're going to have, so you have b subscripted by the letter m. So you have b of m times x to the m plus b of m minus 1 times x to the m minus 1. And have running to a constant b naught. Okay. And for this rational function, okay, so we want to have where n is going to be the degree of the numerator. And m is going to be the degree of the denominator. Okay, so those are the opening defining characteristics. Now, where the asymptotes, horizontal and slant, will come in, this will come down to what results in the degree comparisons. If we have, first of all, if we have that n is less than m, then there's going to be a horizontal asymptote. And that's just going to be y is equal to 0. That is, if the degree of the numerator is less than that of the denominator. Now, if the degrees are the same, if n is equal to m, okay, now there's going to be a horizontal asymptote, but it's not going to be reduced to 0. Instead, what you're going to have, instead of y equal to 0, we'll be looking at y is equal to the ratio of the highest order term coefficients from the numerator and denominator. So this will reduce to a of n over b of n. Now, say you have crossing over for n from less than m to equal to m, to where it is going to be greater than m by 1 degree. Okay. Instead of a horizontal asymptote, there's going to be a slant asymptote. And the slant asymptote is going to be a straight line, okay? And I would normally write this in slope-intercept form, like mx plus b, but I've already used up the m and the b, so just kind of use, say, Greek letters here. So you have y is equal to alpha x plus beta. So like alpha is going to be the slope, beta will be in reference to what y is equal to in the y-intercept. And then for other situations, if we have that n is greater than m by more than 1, what this means is that there's going to be neither asymptote type. So I'm just going to use a little bit of shorthand here. Okay, so you have no horizontal asymptote and no slant asymptote. Okay, so if there's to be an asymptote, it's not going to be a horizontal or one that is a slant, if the degree in the numerator is by more than 1. Okay, so it's greater than by more than 1. Okay, so you have no horizontal asymptote and no slant asymptote. And just looking at what we have regarding domain and asymptotes, so just kind of tying in what we have dealt with so far. And so if I were to determine the domain and the asymptotes, what I'll do here is I'll just present a set of rational functions that will be already in simplified form. So we'll say we have r of x is equal to 3x plus 1 all over x plus 2. Okay, so r of x is already in simplest form. Okay. And for the domain, okay, so again, x plus 2 cannot be 0. So you have the x cannot be negative 2. And for what we have in the case of the domain, okay, so you have those values of x less than negative 2, as well as those values of x greater than negative 2. And since the rational function is already in simplest form, again, x plus 2 remains, and so we'll have a vertical asymptote with x is equal to negative 2. Now, where the other asymptotes will come in, possibly. Okay, so you have r of x is equal to 3x plus 1 all over x plus 2. So now we're stressing the degree of what is in the numerator and denominator. Okay, so you can read this as 3 times x to the first plus 1, and we have all over x to the first plus 2. And if you notice, okay, we have x is our first order, so we can say that n is equal to 1. And guess what? In the denominator, the higher degree term is x, and that is of first degree. So m is also equal to 1. So out of our scenarios here, we have that n is equal to m. So this means that there is going to be a horizontal asymptote and we're looking at taking the ratio of the highest order terms for the numerator and denominator. So you have 3x over x. So that becomes y is equal to 3. So we're going to have two asymptotes. Okay, so you have x equal to negative 2 and y is equal to 3. And looking into the shape of things, for this particular function, r of x, okay, so I have x equal to negative 2. We have y is equal to 3. Okay. Again, there was no cancellation, so there's no hole in the graph of r of x. And the way that this is going to appear, now there can be some functions that will touch and even intersect the horizontal asymptote, but again, vertical asymptotes are going to be off limits. Alright, so these two sections, okay, will be for what we have regarding r of x is equal to 3x plus 1 all over x plus 2. Right. Now another situation, and this rational function is already going to be in simplified form. So we have r of x, okay, we have is equal to 3 over x plus 4, and again, we have x plus 4 cannot be 0, So you have the x cannot be negative 4. So you have for the domain, okay, so you have those values of x less than negative 4 as well as those greater than negative 4. And again, like the prior example, okay, so this rational function is already in simplest form. So with x plus 4 remaining, okay, so the exclusion from the domain is going to be the vertical asymptote. So we have the vertical asymptote at x equal to negative 4. Now, in terms of any other asymptote, okay, so you have r of x is equal to 3 all over x plus 4. Now, if you notice at the top, we don't have an x term. So what does that mean? That means that the degree of the numerator is equal to 0. And for the denominator, okay, so you have from x, okay, so you have x to the first. So we have that m is equal to 1. So in the relation, okay, so n is at 0, m is at 1. So we're going to have a case so where n is less than m. So this will be the first scenario drawn up in comparing the degrees of the numerator and denominator. So n is less than m. So this signals that there will be a horizontal asymptote y is equal to 0. So looking at what we have. So again, the items of interest, okay, so you have x equal to negative 4. And again, we have y is equal to 0, and that is going to be the x-axis. Okay, so you have two asymptotes, and for r of x, okay, the way that this graph is going to behave, okay, so you have section up and to the right. You have another section, so this is going to be down and to the left. All right, now, in the case of a little bit of a change up, I think one reason I'm throwing this in is that, like, you might have a special case with Alex for a problem of this type, and this one, in a sense, is kind of tricky. Here we have r of x. We have is equal to x cubed plus 3x squared plus 4x plus 1, okay, and we have all over x squared plus 1. Okay. Now if we're looking for the domain, again, Now the denominator cannot be equal to 0. X squared plus 1 cannot be 0, so we have the x squared cannot be -1. And guess what? We're trying to find out what is going to be restricted. And guess what? Utilizing the square root property of equality. Okay, so you have going from x squared to x and -1 to its plus or minus square root. You're only going to have complex numbers. So what this means is that there are no real values excluded. Okay, so this is going to mean a couple of things here. With no real values excluded, that means that the domain is going to be the set of all real numbers since there's no real value that is left out. Anything left out is only in the complex numbers. And since there are no real values excluded, and guess what? There are no restricted values, so that means that there will be no vertical asymptote. For there to be a vertical asymptote, something has to be restricted from the real number system. And since I have only complex numbers, there will be no vertical asymptote. Now, regarding this ratio, okay, and see if we have any kind of asymptote period. So we have, in the case of the numerator, so we have n is equal to 3. And we have the m is equal to 2. And just in the setup here, so you have n is going to be greater than m. 3 is greater than 2 by 1. So you're going to have a slant asymptote. Okay, so you're going to have a straight line, and then looking at just what y is going to be equal to. So we can perform polynomial division. Now if I had the divisor to be x plus 1, I could have performed synthetic division, but since I have the divisor to be x squared plus 1 as opposed to x plus 1, let's say I'm looking at long division instead. So again, we have x cubed plus 3x squared plus 4x plus 1. So I don't have any missing degree terms from the dividend. Okay, so for what we have here, if I take x squared into x cubed, x squared into x cubed x times, so you have x over x squared plus 1. So this will be x cubed, and x over 1 becomes x. And with long division, again, I'm looking at row by row subtracting. So we have x cubed will go out. Notice that 3x squared is untouched, so I'm going to bring this down. And we have 4x minus x. Okay, this will leave us with 3x. And then we have the plus 1. Now we have x squared into 3x squared. This will go 3 times. And distributing, so we have 3x squared plus 3. Okay, so we have 3x squared will go out, and the only thing left standing, okay, so you have 3x, and 1 minus 3 becomes negative 2. Okay, and I cannot take x squared directly into 3x. So in terms of the quotient, okay, so you have x plus 3, and your remainder would be 3x minus 2. So we have, in the case of the slant asymptote, I'm interested only in the quotient part of this. So there's going to be a slant asymptote, and that is going to be at y is equal to x plus 3. Okay, so once again, okay, x squared plus 1 could not be 0, and there is no way that it could be 0, since, at least not in the real number system, and the only values excluded were just from the complex numbers, so there are no real values left out. So that means that you can plug in anything for x, whether it's 0, positive real number, or a negative real number. So the domain is the set of all real numbers. And for what we have in the case of taking, again, we have no vertical asymptote since there were no real values excluded. And again, we had a 1 degree difference between the numerator and denominator. So you have a slant asymptote, and again, the what y is set equals is going to be set equal to is going to be the quotient from performing the polynomial division between the divisor and the dividend. Okay, so we had that quotient at x plus 3, and we're not worried about the remainder. So there's only one asymptote, and that is going to be at y is equal to x plus 3.